When we started our discussion about memory and the memory hierarchy, we talked about something called addressing, addressing methods or addressing modes, how we address or find what we're looking for at different levels of the memory hierarchy. And at the bottom, in long-term storage, we talked about sequential and direct addressing. In main memory and all of the things that are in the memory map, we looked at random access memory, RAM, which most people associate with the DIMMs you stick in your computer. RAM is actually an addressing mode where I give a pattern of ones and zeros and I have access to a specific memory location within that full memory map. Caches were different. They used something called associative addressing. And that meant that associated with every piece of data or instructions, the element that is inside of the cache, we have associated with it some identifier that shows where it came from in RAM. Now there are three types of memory. There's three types of associative addressing modes or algorithms. There's fully associative, there is set associative, and there is direct. And we're going to talk about all three in three different lessons. But fully associative is, in my opinion, the easiest to understand. So we're going to start with the associative, the fully associative addressing algorithm mapping. Let's try that again. We're going to start with the mapping algorithm called fully associative. So, fully associative mapping algorithm. Now, to begin with, let's review what the insides of a cache looks like. If you recall, if we've got a cache, it is divided into lines. Each one of those lines contains two basic components. They have the tag, and then it also has the element or the block of data that we've brought in from memory. And so remember, when we are talking about bringing in stuff from memory into the cache, it was really important to know that that locality of reference or principle of locality, whichever one you want to go by. And it said that if I use something out of memory, I'm probably going to use it again real soon. Notice the word probably, but still, I'm probably going to use it real soon. And also that if I use something from memory, I'm probably going to use its buddies too. So when I bring something in from memory, why don't I bring in a bunch of pieces? And we talked about how we did that by saying, okay, we have the full address, right? So that is the full address as being referred to when we're using RAM, the random access memory, so the binary pattern of ones and zeros, right? And we separated a couple of these bits toward the end, and we identified those as the word ID, or the word ID bits. And then these bits we identified as the block ID. Now, what the purpose of the tag is, whenever it comes to referencing or figuring out where that block came from, there is an algorithm, one of these three algorithms, that we use to associate that tag with the block ID, where it came from in memory. Now, fully associative mapping, it's pretty easy. All you do is just simply take the block ID and store it as the tag. Well, great. Well, what does that tell us about the word ID? Well, the word ID is used to figure out which element in the block it is. So let's try this from scratch. If I've got a processor that needs an element from memory, it needs to access it, instruction, data, reading, writing, whatever, but it needs to access it. What it has to do is give a pattern of ones and zeros that represents the address that it's looking for in main memory. We'll talk about virtual memory later, but whenever it's giving a pattern of ones and zeros that represents the address. Now, in fully associative memory, what it does is it looks, the cache hardware takes the block ID and simply compares it to every single one of the tags. Now, it doesn't do this all it doesn't do this sequentially. It doesn't go through the list one by one by one. That would make the cache incredibly slow. What it does is it takes that block ID and has hardware so that it can do all at one time, an instant compare of that block ID with all the tags. Now, in a properly operating cache, there should be only exactly one line that matches that block ID, or no lines that match the block ID. If there are no lines that match the block ID, that implies that it's not in the cache, and we need to go all the way out to main memory, our next level, to see if we've got the data out there. All right, so let's just do a scenario. Let's just say that I have my full address, and we're going to just have an example here. We're going to say, I don't know, how about 12 bits? All right. And then the word ID, we're going to have this in our example of 2 bits, which means the block ID in our example is 10 bits, right? All right, so that means that, let's just say that, and let's go back to this diagram of our cache. Since we have 2 bits for our word ID, and 2 bits, there's 4 possible patterns of 1s and 0s we can have, then that means that in every line, we are going to be storing 4 data elements. 1 for the word ID 00, 1 for the word ID, and I didn't leave a whole lot of room here, 01, 1 for the word ID 10, and 1 for the word ID 11. All right, now, let's say that the processor, and with 12 bits, yes, I realize that's an incredibly small memory. It's 4K. There's not a lot you can do with really 4K anymore. But if we've got a 4K address, so maybe what we've done is the processor wants to access the value 12 bits. That's 3 nibbles. That's 3 nibbles. So at, let's say, 43F. That's what it wants to access. So we convert 43F, and that becomes 0100. That's the 4, and then 3 is 0011, and then F is all 1s. Now, if we are to look at this guy as the full address, but then divide it, what we've got is we divide right at this point. And so we have the word ID of 11, which means that whatever element we're looking for, it's going to be found in this last column. This right here is the block ID. So the 10 bits here, 01000, 0111, 4 ones there, that's going to be our block ID. Now, we go to the cache. Now, when we first fire things up, there's nothing in the cache. The cache is empty, so we've got to start filling it. So we go out, it's not in the cache, so we have to go out to memory. Now, main memory comes back and says, yeah, here are the 4 elements that are in that block. So we take the 0100001111. There's the tag that is associated with that block. And then the 4 elements, and I'm just going to make up 4 elements. Let's just say A, B, D, 5, 9, F, 1, 2. Okay. Now the 1, 2 is actually what we were looking for. That's the value that was being returned. But we also brought its buddies because we knew that it probably would be needed. They probably would be needed. All right. Now, the next time we access, let's say that the processor says, okay, I need 5D2. All right. Goes out to the cache, and it does the, in binary, we've got 5, and then D, and then 2. All right. Hopefully that was a correct conversion. And so we divide it into the block ID and the word ID. And the block ID, it looks through the list and it doesn't find it. So it has to do what we do, go all the way out to main memory in order to grab that. Now it goes out to main memory and it puts the block that is returned into the next line of the cache. And so, I don't know, how about 5391 FAB2. All right. So we've got more data. This is just all coming from the RAM, right? the random access memory map. Now, the data that we were looking for is in the 1, 0, associated to the 1, 0 column. So that block identifies this line of the cache, and then the 1, 0 says it's in this column, so it's FA. All right. Sorry, we're going to do a couple more. Now, whenever we do, I don't know, how about 0x, 4, 3, and we'll do D. All right. Now, 0, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, 1. There you go. Now we divide this into its block ID and its word ID. And we look at that and we take that block ID and we compare it and we go, oh, we found it. So we don't have to go out to main memory. But which one of these 4 elements is it? These last 2 bits identify it as being in this column, so we return the D5. The correct tag intersecting with the correct offset into the block gives us D5. All right, so that's really, in essence, how a fully associative cache works. But there are a couple of other things that we need to talk about. And to talk about that, let's go ahead and fill out the rest of this table. So, a question I might give is, well, let's see. The processor is looking for the value at EEA. What is it? Well, first of all, EEA, that being the address. Let's go ahead and do the conversion. Let's make some room. So hexadecimal EEA is 111011101010. All right. Now we divide this into the word ID bits and the block ID bits, right? And we take that block ID and we compare it to all of them, and we see that we actually have, no we don't. Let's see. Oh, I'll tell you what. Let's make this EE. I had one too few bits here. So let's try this again. Let's assume that Tarnoff put a 0 there. So we have EE10. So 1110111010, 1110111010. So it's in this row. We found the tag. There are probably other tags there that I've only got 9 bits for instead of 8. Well, in fact, the one right above it. All right, now, so this has identified this row, and then we use the word ID bits to figure out the offset, and we see it's this 33. And the cache returns the 33 in a much quicker fashion than if we had to go all the way out to main memory. Now, let's say that we go ahead and ask for B2B, which is 1011, 0010, and then 1011. And we go through the list and we see, well, we got something that starts with a B here, but you know, close isn't good enough. It has to be exact. So we don't have it in the cache. So we go out to the main memory, fetch it, grab what we're looking for in main memory, and we bring the block in and oops, we don't have a place to put it. Well, that brings one of the issues when it comes to fully associative mapping that one of the other mapping algorithms doesn't have, and that's the idea that we need to throw something out sometimes. You know, what we're trying to access, it's not in the cache, but there's also no room. Eventually, if the processor's been running long enough, it'll fill up, right? And so we need to have something called a replacement algorithm. Let me go ahead and erase this a little bit, make some room so that we can talk about replacement algorithms. All right, replacement algorithms. And once again, I think I'm going to be limited by the space I've got on my board here. But let's go ahead and try and at least enumerate the 4 of them that we're worried about. First of all, there is first in, first out. You've probably heard of this. A lot of buffers use this method in that the thing that's been in the longest, that's the first thing you take out. And that's really how this cache algorithm works. And so we replace the block that's been in the cache the longest. Sorry about my squeaky pen. I selected it. We're stuck with it until I'm finished with this. All right. So replace the one that's been in the longest. And what does that really involve? Well, there's a couple of ways you can implement this. Basically, what you've got is just a list as we've populated those lines. And as soon as we find out that we don't have room, then the one that's at the very back of that list, whatever line that is, and in the case of how I first populated this, it'd basically be this first line. We throw that out. Now, what's the problem with first in, first out? Well, just because it's been in the cache for a long time doesn't mean that we don't need it. For example, what's the very first thing that gets loaded? Well, operating system routines, right? And so if your operating system is loading routines at the very beginning, just because they were loaded first doesn't mean they need to be thrown out first. You might want to keep those around. So we've got another one which is much better. It's a much better performing one. And this one is called, and I'm going to put the initials up here, but I'll say what they are. They're the least recently used. All right, LRU. Replace the block that's been least recently used. All right, so you've got the LRU, right? Now, that one's a little bit better because if some data or something that's in the cache has gotten stale, well, not been used for a while, probably a good chance that we have gone past the time whenever we were executing that code. Go ahead and throw it out. Replace that one. So what does it involve in terms of implementation? Well, there's a number of ways that we can implement this too. But when it comes to a fully associative cache, what you're really going to do is have either a timer that's associated with every single one of these, so that every time we access the cache, all the timers increment except the row that was accessed, reset that one back to 0. And so every time you access, increment all the timers, reset the one that was accessed. And whenever it comes time to replace something, to throw something out, all you got to do is just look at the timer that's got the largest value in it, right? You could also do it with some sort of a list once again. And anytime something's used, you just put it back at the end of the list. And every time something's used, put it at the end of the list. And whatever's at the front of the list, that's the thing that's been least recently used. Now there's another option which is not really very popular because it's not really very effective, but it's called LFU for, well, we replace the block that's been least frequently used. All right. Now, the performance of this one, and to be honest with you, I've not seen an implementation of this very often. The performance of this one could be hurt because you may have had something that was used in a lot, and it hasn't been used for a long time. That application is gone. Now, when it comes to like a multitasking operating system, something that has the ability to run just about anything, least frequently used doesn't perform very well. But if you've got something more like an embedded system, something that has a very mission-specific code, then it may be that since there's only one piece of code that's really being used here, and the portions of that code that are used a lot are going to continue to be used a lot throughout the lifetime of the product, yeah, maybe least frequently used is an option. But I'll tell you what, the fourth one actually has some significant benefits. The fourth one's going to seem kind of simple. It's called random. Just pick one, right? Throw something, just pick something, throw something out. Now, it turns out that in simulations, random does not perform all that worse than these other algorithms. And the really cool thing about it is that all it requires is just a random, some sort of a random number generator that's on the chip that most chips come with now, just some sort of a random number generator. It just picks a line, throws it out. Now, why would you pick this whenever these, at least these first two, will perform better than random? Well, it turns out that because this one's so simple, it's really cheap and low power to implement. In other words, the processor itself doesn't have to go through a lot of computation in order to figure out which one. So if you've got some sort of a device like a cell phone or some sort of an IoT device that's running on a battery, maybe it'd be a good idea to pick random because you're not necessarily going to get much lower performance, but you will save on power. It also is cheaper. If that's the only replacement algorithm that you've got in your device, it's cheaper because it'll take fewer transistors or use transistors that are already being dedicated to that same function. Now, a lot of the processors I've seen give you options. So, for example, they may give you an option between least recently used and random. And once again, you can pick that to decide what's best for your application. Now, that brings us to kind of the wrap-up in terms of the fully associative cache. But let's talk for just a moment about the fully associative cache the benefits and the drawbacks. Now, the benefits. First of all, and we haven't talked about any of the other mapping algorithms yet, but one of the things that's really important is that as far as all the mapping algorithms, this one has the least chance, in fact, it has no chance, of thrashing. In other words, throwing out a block and replacing it, but then finding out you need that block again and bringing it in and throwing out something that's needed back again, and this thrashing back and forth, throwing something out to main memory, bringing it back in, throwing something out, bringing it back in, that can actually significantly hamper performance. And as far as fully associative caches are concerned, there's really no thrashing at all. But we do have two drawbacks. First of all, they're expensive. Why are they expensive? Well, the reason they're expensive is because whenever we do come up with that block ID and have to compare it to all of the tags, so we're comparing it to all of the tags, bam, at once, that takes a lot of hardware to do. And so that makes it very, very expensive. There's basically a compare operation being done on every single one of those tags with the block at one time. Very expensive. Not only that, but think about this. Doing all of that operation all at one time also makes it slow. So as far as the cache algorithms are concerned, the cache mapping algorithms are concerned, we've got no thrashing with fully associative caches. We'll talk about thrashing when we get to direct mapping, but it comes at a cost of it being expensive and being kind of slow. All right? Fully associative, my opinion, the simplest to understand, but maybe not the best to implement.